Okay, so let's go ahead and get started. This is Math 2305, Discrete Mathematical Structures. This course is designed for computer science majors and data science majors. And it's going to be a different math course than what you've taken in the past. We're going to deal a lot with logic. We're going to do some programming, and I'll get into that later. And I'm looking forward to it. But first, I want to tell you a little bit about myself. So my name is Dr. Randy Davila. I am an assistant professor of data science here at UHD, but I'm also alumni. So I graduated from UHD with a bachelor's in applied math in 2012, I think. I was the first person in my family to go to college. So that was kind of a big deal for me, and UHD really helped me. So I have a soft spot for UHD students. After graduating at UHD, I went to Rice, where I got a master's in computational and applied mathematics. And after that, I finished my PhD in mathematics from the University of Johannesburg in South Africa. And that wasn't that long ago. I finished my PhD in 2019, I think. It wasn't, yeah, 2019. But I've been lecturing at various universities throughout this time. So I've taught courses at Rice. I was a lecturer at Texas State University for 3.5 years. And then after that, I was a lecturer at UHD before I became an assistant professor. And one of the courses I've always taught has been discrete math. And that's because my PhD and my master's all focused in a subfield of discrete math called graph theory, which we'll get into that much later in the semester. So that's a little bit about me. I'm going to put my CV up on Blackboard so you can take a look at it. Speaking of, let me share my screen with you. Not that one, this one. Okay. Okay, so here's my screen. So I'll move this. Actually, let me do this. Okay, so can everyone see my screen over here? Everyone can hear me, right? Sometimes the audio is okay.
Yes.
Okay. All right, so here's the Blackboard page, and the syllabus has been posted. So the topics we're going to cover, we're going to start with logic and what is called proofs or mathematical proofs. Then we're going to go into a branch of math called set theory, then number theory. We're going to start talking about programming somewhere around number theory, and then talk about what's called object-oriented programming. And we're going to get to algorithms and complexity, and then finally we're going to have applied graph theory. Now, when I say programming, I mean we're going to be using the Python programming language. Now, if you've never programmed before, or if you've never programmed in Python, do not worry. I'm going to post a lot of material for you to learn this on your own, and I'm also going to provide my own programming instructional videos. But more about that later. So the homework is going to be a big chunk of your grade, and that's going to be assigned through the Discrete Mathematics book, which is required for this course. I posted instructions on how to get to this. So course content here. So these are the instructions for your book. It's 58 bucks, which is pretty cheap for math textbooks. And when you log on, you'll see something like this. I haven't created any assignments yet, but I will later today. And you come in and you just click here and you start working through, and it's an interactive textbook. So I think that's kind of nice, especially considering that we're going to have this course completely online. So as you're going through, there's little assignments that you'll do, and there's animations that kind of express the ideas behind the sections, which I kind of like. So the homework will be important. It's 50% of your grade. We'll have 2 exams, and these exams will be obviously take-home exams, but they'll be what I call pledged exams. So they'll be timed, and you'll be allowed notes, but you won't be allowed to talk to anyone while you're taking these exams. They should be fairly straightforward, and again, they're only 15% each. Now, the important thing here is the final project. The final project will be a group project. You can do it on your own if you want to, but I highly encourage you to work with others on the final project. And this will be a programming assignment. So basically, you're going to use Python to program a algorithm that is common to be asked about in programming interviews, if any of you have ever heard of anyone doing that before. Okay, so everyone will need to install Anaconda on their machine. So there's a link here. If you click this, you'll be brought here, and then products, individual edition, and then download. So when you download Anaconda, what it's going to do, it's going to install the latest version of Python. Oh, by the way, I just saw that someone asked about GroupMe. So before I continue with Anaconda, please make a GroupMe. I found that that's really useful for these online courses, and feel free to add me to it. That way, if anyone is having problems on an exam and it's a weekend and you can't get a hold of me, you can just send me a message on the GroupMe and I'll get it on my phone and I can respond immediately. So please, someone make a GroupMe and then add everyone in the class, and also add me. That way, if there's an emergency, you can get a hold of me. If anyone gets sick, if there's a COVID-related anything, it's just important that y'all have a way to get a hold of me if there's an emergency. Okay, so back to Anaconda. When you download Anaconda, it's going to install the latest version of Python together with a suite of IDEs, or integrated development environments. These are just ways to interact with Python. And it will also install every Python package that you will ever need. So it'll look something like this. I'll go ahead and open it for you. So I already have Anaconda installed. To take a second to load here. So these are all the standard packages that it will install. No, these are the IDEs. So Jupyter Notebooks, Spider is what we're going to use. These are pandas. I mean, these are packages over here. Oh, it's on my other screen. Where is it? Oh, there it goes. Okay, so when you open up Anaconda, it will look like this. And we're going to be using Spider as our primary IDE. And this is just a way to interact with Python. Okay, so I'm going to launch this. It's going to take another second. goes, opening up. Okay, so when it opens up, it will look like this, or some variation of this. Okay. I've kind of changed around a few things. Now, when you install Spider, or when you install Anaconda and you open up Spider, what you'll want to do is you'll want to go to Projects, New Project, and then name this, say, something like Math 2305, Fall 2020. Notice the underscores never put spaces because what this is doing is it's making a directory or a folder in this location right here. So I have this folder right here that it's going to create. It's going to be an empty project. And I create it. It's going to take a second to make. All right, thank you for making that group me. I'll join that when I get a chance. So now that you've created this, see over here, you'll see an empty folder, and you'll see ways to interact with Python. So over here, you can have like 1+1, like a little calculator type of thing. Make a print statement. And you can just start to play around with Python now. You won't need to learn Python for several weeks, but I encourage you to start playing around with it now. And this is the easiest way to interact with it. And I'll post at least one video this week just to get you started. And on that note, actually, if you go to Blackboard, you'll see YouTube videos here. And this will constantly be updated. I find YouTube videos all the time related to both programming and discrete mathematics. But related to programming, if you click on this one here, this will open up a video series by Corey Schaefer. Now, Corey Schaefer is, in my opinion, is one of the best ways to self-teach Python. His videos are very detailed, and you can pause them over again. And he starts in the very beginning in this video series. And you see that these numbers here, there's a list of videos that he has. I go back over here, you'll see that I have suggested videos. So 2 through 9, 19 through 22, 40 through 44. If you complete all those videos on your own and you program with them, you probably won't even have to watch any of the videos that I'm going to make. Just because they're that good. I really do enjoy them. So please watch those. There's also anything that I post in the YouTube video section you should probably watch. This one right here is a course I found on discrete mathematics. It's going to be very similar to the topics we're going to cover. So for example, in our first week class, we're going to cover 1, 2, 3, and 4 probably. So like those 4 videos is like the first week and a half of class. And then 7, 8, 9, 10, probably be the second week of class. 11 through 15, probably the third week of class. Actually, probably all the way up to 19 or 20 by the third week of class. And these are really good videos, and the notation and the terminology that they use is going to be very similar to what I'm going to do. So If you need supplemental materials, please visit that link. And again, anything that I post in the YouTube videos folder, you probably should watch because it'll be related to what we're doing. Okay, so what else is in here? So install Python, watch the YouTube videos, purchase the Zybook, and for the first week, I'll make an announcement, but it looks like the first week is going to be so 1.1 through 1.4. And the first homework will probably be due next Wednesday. Okay. So this is probably new for a lot of us, and this is my second time teaching fully online. All my courses are online this semester, so bear with me. I'm going to try my best. If there's anything that I can do that I'm not doing, I would really appreciate it if all of you gave me feedback. That way I can make adjustments early on, so I'm not like teaching y'all poorly throughout the semester. Okay? So that was the, I guess the introduction to like the course materials. Now I want to talk about why all of you are in here. So if you can, in the Zoom group chat, just everyone list their major. I'm curious to see it. All right, so it looks like so far, so it's like 75% computer science, maybe like 15% data science, which that's pretty exciting, and the rest of the percentages are other majors, right? So, does anyone have any idea what discrete mathematics is? You can answer over here in the group chat. Any idea? So get a no here. In logic and proofs, okay, logic gates. So, it's very rare that people will know what discrete mathematics is. In fact, I can always tell in conversation if I ever say anything like I say the term discrete math, and someone says like, "Oh yeah, that," like they talk to me just a little bit about it, I automatically know that they're either a computer science major, a data science major, a math major, or a stat major. It's very specific to these disciplines, but it's especially important to computer scientists and data scientists, and there's a reason for that. So, okay, we're gonna do a little bit of review right here. So, we're gonna review the sets of numbers that exist. So, the first set, what we call the natural numbers, and that's the set denoted with this funky looking N. And that's the set of numbers 1, 2, 3, 4, off to infinity. So those are the naturals. And these are sometimes called the counting numbers because you use them to count things, right? Okay, so then we have the integers. Which is denoted with this z. So that's going to be dot, 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 2, 1, 0, 1, 2, off to infinity. So it's the positive and negative natural numbers together with 0. Oh, and these are curly braces, by the way. Messy. Those curly braces just say that we're denoting a set of objects, and we'll learn about that in a few weeks. Okay, so we have the naturals, the integers. Oh. Sorry, I lost my signal. Okay, y'all still hear me?
Yeah.
Yes.
Can't see you.
All right. Okay. Second.
Okay, cool. Thank you.
All right. Sorry about that. Okay, so next we have the rationals. Noted with a Q. Okay, now I'm going to write this down first, and then I'll explain, I'll read it out for you so you can understand what's happening here. Okay, so this is called set builder notation. Looks like a lot, but it's not so bad. Okay, so the way that this is read, so this is the set. So anytime you see curly braces, you're entering into a set. So this is the set of all A over B, okay? And then here, right there, that just means such that. And so the colon means such that. So the set of all A over B such that. And then this right here, this just means such that A and B are in the integers. So they're elements of the integers. Okay. All right. This is just the AND symbol. And B not equal to 0. So the set of all A over B such that A and B are integers and B is not equal to 0. Okay, so some examples of rationals would be something like 1/2, right? Because that's an integer, and the denominator is not 0. So that should belong in there. That's a rational number. Another one would be like -3. -3 is irrational because that's the same thing as saying -3 over 1, right? So that's a ratio, so that would also be irrational, okay? Now, so every integer is also irrational. That's one thing to note. But every ratio is also inside of the rationals. Now, that's a lot of numbers. These are all infinite sets, right? But what are some other numbers? Like, it almost seems like every number should be inside of there, right? But are there other numbers? Like, can someone think of a number that can't be expressed as a ratio? I see someone said irrational number. But how do we know there's something that is that is irrational that doesn't exist in there? How did we ever discover those things? Well, I'll show you the first one. So,
Maybe like a square root.
okay. All right, so just gonna say, just gonna write this down so we can remember what it is. The set of all A over B, such that A, B are integers, and B is not equal to 0. Okay? So, the first number that was ever discovered that was not in there it came from this cult called the Pythagoreans, and this was a cult, a religion culty type thing that existed during the time of the Greeks. And they worshipped ratios. They thought that everything in nature was some type of ratio. Until an unfortunate man considered this right triangle. So that has length 1, that has length 1. If you use the Pythagorean theorem, you see that this hypotenuse has to have length square root of 2. And the reason why I said unfortunate man that discovered this was because that turns out to be not rational. That does not live in there. And the rest of the Pythagoreans, I think they murdered him. It's not like 100% sure, but I'm pretty sure they killed him for finding that.
Oh my God.
So, but okay, a part of discrete math is dealing with logic and argumentation. So we need to be able to tell why that is not rational. We need to give an argument why it's not rational. Okay. So I'm going to give you the first proof that you've ever seen. Now, bear with me on this. I'm assuming none of you have the background to really understand what I'm about to do, but we're going to get there. This is, it's going to seem intense, but trust me, the proofs that you're going to do at first are not going to be anywhere near this. So this is what's called a theorem. It's a true statement. And it says the square root of 2 is not rational. And for those of you that enjoy mathematics, a proof of this theorem that I'm about to show you, most mathematicians would consider as one of the most beautiful proofs. It's very simple to a mathematician. It won't be to you, but we'll get there. Don't be afraid. It's very simple. It was the first type of argument this way, and attributed to Euclid. Euclid was, of course, a very famous geometer. Okay, we have a theorem. We're going to prove it. All right. So the way that this is going to go, we'll say proof. Okay. Now, what I'm going to do is I'm going to assume that right there is rational, right? Like, what happens if I assume that it is, right? So right now we're assuming that it's not, like, the theorem says it's not rational, but I want to assume, okay, maybe it is. So, so what I'm going to say is, by way of contradiction, we'll learn what that means later. way of contradiction. Assume the square root of 2 is rational. So that epsilon right there, that just means is an element of the rationals. It's in there. So we're assuming the opposite of what we're trying to prove. And the hope is that when we assume that, we're going to get something that doesn't make any sense. Okay? So if we assume that that number, square root of 2, is actually rational, it better be in there, right? It better look like a ratio somehow. Right? So if under this assumption, right, we can use the definition of being inside of there. So then we can say, then, by definition, the square root of 2 is equal to a over b for some a and b that are rational numbers and b not equal to 0, right? Like, if we assume that that is in there, right, then it must be the case that square root of 2 can be written as a ratio of some integers, right? Okay. Now, here's an important thing that we need to assume. So, like, okay, it's a ratio of integers. What's more, we can assume that a over b has been simplified as much as we can. Like, otherwise we could. Like, if it was like 3/6, we could simplify that to what? 1/2, right? So we're going to assume that we've already simplified it as far down as it can go. So I'm going to write that in green because it's really important. So further, we assume a over b well, what's another way to say that something's been simplified and we can't go any further? Another way of saying that is that a and b have no common factors, right? Like, if that has been simplified all the way, they don't share any common factors. Otherwise, we could have simplified it, right? So we may assume a and b share common factors. Since otherwise we didn't simplify it all, right? Okay. So square root of 2 looks like that, right? So I'm probably going to have to divide. This isn't going to be a formal proof because I don't have enough room right now. So I'm going to say maybe so. I'm going to do some algebra over here. Square root of 2 b means that 2 is equal to a over b squared, which means it's like a double arrow. For both sides of that equation, I get that, which means that 2 is equal to a squared over b squared, which means that 2 times b squared is equal to a squared, right? That's just some algebra. I square both sides, I get that. the square ratio is the ratio of the squares, and then I multiply it by b squared and I get that. Okay? So now looking at this, right? A squared is equal to 2 times b squared, right? Well, what that means, right, is that a squared is a multiple of 2. So what this means is that a squared is even, right? Because to be even, you're a multiple of 2. So since a squared is equal to 2 times b squared, a squared is even, right? So I'm keeping the algebra over here just to save room. I would normally not write this proof like this, but I have a tiny whiteboard now, so I have to. So a squared is even. Okay, not that algebra stuff. Okay. If you think about it, right? Like if the square of a number is even, then it must be the case that the original number was also even, since otherwise, how did a factor of 2 get into the square? You're just multiplying by yourself, right? So a squared is even. So this is algebra stuff right here. And a must be even. Right? Like if the square of a number has a 2 in it, then that means there had to be at least 2 2's in there. Right? So we've concluded that a must be even. All right? So far, so good?
Why is A even if A squared is even?
So a, do you understand that a squared must be even?
Yeah.
Okay, so let's just write it that way. So 2 times some number is equal to a squared, right?
Okay.
But that's just a times a, right?
Right.
So if a didn't have a factor of 2 in it, then that doesn't have a factor of 2 in it. Where did that 2 come from? Right?
Okay.
That make sense?
Yeah. Yeah.
Because there has to be a 2 there. So yeah, so this is, so we know that there has to be a factor of 2 for a if there's one in the square.
Okay. I see.
So the definition of being an even number is that you're 2 times an integer, right?
Right.
Let's just say let a equal 2 times some number. Pick a letter, any letter.
T.
T. So where t is some integer. So a is even, so we can write it like that. We don't know what t is, we just know that there is an integer that does that.
Okay.
So going back over to this equation here, we have 2b squared is equal to a squared, right? But if that's true, double arrow thing, then b squared is equal to a squared over 2, right? Okay, but we know what a looks like, right? A is just 2 times some number, right? 2t. And like, all I did here is I replaced that a by its other form, that. That's all I did. So if we work this out, 2t all squared is 4t b squared over 2, which means that b squared is so 4 divided by 2, here, c squared. Okay? So we just worked our way back down. Okay? So what do we know about b squared? B squared is even. Right? Because it's 2 times some number, right? But just like the argument before, if b squared is even, it must be the case that b is even. Okay? Okay, we've gone a long way, but let's see what we've learned. Look at everything in green, including the sentence in green. Anyone see a problem? By the way, we want a problem. I see someone getting close over there in the comments. How can all of these things happen at the same time? Y'all are getting it. A and B share no common factors. But if that's true, then we get that that's true, which means that A must be even, right? But if A is even, then we can write it like that. And from that same equation, which if that's true, that must be true. So then we can kind of manipulate out and we see that, oh, B squared is even, but then B is even. So how can they share no common factors, yet A is even and B is even? This means that A has a factor of 2. This means that B has a factor of 2. They can't all be true, right? This is a contradiction, a false statement. That finishes the proof off. Why does that finish the proof off? Because this statement is either true or false. And as we'll learn in the logic section, so this is called a proposition. What was that contradiction? We assumed the opposite of this statement. And all propositions are either true or false. So if a statement is true and the opposite is false, the opposite must be false. If a statement is false, the opposite must be true. So here, we have something we want to show to be true. We assume the opposite of it, and then we get something that's false, right? So we assume this, and we showed that this is false, which means that the original statement is true. So that's how the theorem is proved. Now, okay, so lots of stuff going on. Don't be too afraid of all this mess right now. It's just, we're going to start from the very bottom and work our way up to being able to do something like that.
What is that square for at the bottom?
So this square represents the Q, E, E, right? Which is an abbreviation for a Latin phrase, quod erat demonstrandum.
Okay.
It roughly means, translates
Error
to,
demonstrated.
yeah, what was to be demonstrated. So we have a theorem and then we write proof. We give our argument, and that's our stamp of approval. What was
Okay. I see. Thank you.
I actually have that right there. Yep.
Nice.
I told myself I would get that when I finished my PhD. So the day I submitted my dissertation, I went and got it done. Okay, all right, so how does this relate to discrete math? We just proved that there's something that's not in there, okay? But why did I do this for you? Well, the reason is that I needed to distinguish that there are numbers. I needed to prove to you that there's numbers that aren't in there. Okay, so there are irrational numbers. Irrationals. Not in Q. In these numbers, together with the rationals, make up the real numbers. So numbers are rationals together with, that's the union sign, the irrationals. And the real numbers are what you're used to working with when you take like a college algebra course or calculus course. That's the number set that you're dealing with. Now, suppose like we're trying to construct a number line. Like so, the Cartesian plane that you're used to seeing, right? That's like there's a number line this way and then a number line this way, right? So if we tried to make a number line with the rational numbers, like 0, 1, 2. Now, in between 0 and 1, there's all kinds of rational numbers. Like here's 1/2, 3/4, 1/4, 1/3. There's all kinds of rational numbers in between 0 and 1. There's infinitely many of them, right? In fact, there's infinitely many rationals in between all of these whole numbers, right? But there's still holes, and there's holes all over if you don't include the reals. So this would be like a number line of the rationals, and then a number line of the reals would be so these are like positive. I don't know if I draw on the other ones, right? But notice how I've drawn these. The rationals have all these holes in them, and the reals fill them in. This is the distinction. There are so many irrationals. There's way more irrationals, and we'll prove this later in the semester. There's way more irrationals than there are rationals. There's so many that when you line them all together in a line, there are absolutely no holes. It's smooth. It's what's called a continuum. This is a continuous line. So this right here, this is continuous. Because there's no gaps in it. This is a discrete line. So discrete mathematics deals with objects that can be placed in non-continuous packets. So it's called countable sets of things, or finite. So discrete is, and we'll learn what this means. So countable and finite sets. That's what discrete mathematics studies. So countable and finite versus continuous. Continuous mathematics is, there's no gaps in anything. You have these smooth looking functions, whereas discrete, you have packets of information that you study. And the techniques used to study these things are completely different. For example, if you think to calculus, right? When you take a derivative of a function, or a lot of continuity of the function is required. You need smooth looking functions, right? So you're allowed derivatives. They exist with continuous sets like this. The derivative is not defined whenever you have packets and it's not smooth. So the techniques used here are completely different than the techniques that are used here. So why would there be so many computer science and data science students in this course? Like, why do you need to be concerned about the techniques used with countable and finite sets? No. Right? Like, so isn't a computer, so there's a finite number of instructions, not a memory, right? The finite,
Yeah.
someone's mic is on. Right, so basically, a computer is a discrete object, right? It's a finite set of instructions and a finite amount of memory. So the techniques used to study discrete math actually helped invent the computer. The first computer scientists were not computer scientists, they were discrete mathematicians. And through working with the theory of discrete math, envisioned what a computer would be and then set out to build one. So in order to understand complexity theory of algorithms and understanding how efficient algorithms work with a computer, you need to understand the techniques of discrete math in order to do that. So, and this is important. So for example, square root of 2 is an irrational number. Pi is an irrational number.
Euler's constant.
Right. These numbers, since they're irrational, they have an infinite, non-repeating, somewhat random decimal expansion, right? You can't express them as a ratio, so they have this infinite decimal expansion with no repetition, really. This is a problem, right? This means that we can only, so if we're going to store pi in a computer, we're not actually storing pi. We're storing an approximation to pi because it has an infinite decimal expansion with no repetition. Computers are finite, we cannot store that in there. So what does that mean? Well, imagine you're working for like NASA or something, and you're dealing with these equations of physics where pi pops up all the time, and you're performing some simulation or calculation using a computer to predict where this rocket you're going to shoot is going to go, right? Well, if that equation has pi in it and you use your computer, you're going to incur a little bit of error. The first time you run that simulation, the first time that number appears in the equation, you're going to have a tiny bit of error, right? Which is okay. But if this is iterated over millions, billions of times, that little bit of error incurred, because computers can't store irrational numbers, that little bit of error is going to start to blow up. And your rocket could end up like going into the sun instead of the moon, right? So I think that that's like a prime example of understanding the difference between like discrete and continuous objects comes in, because then you have to make adjustments to your simulation or to your algorithms. That's a branch of mathematics called numerical analysis. In fact, when you go to Blackboard and you watch the map of mathematics, I'm going to post another one, the map of computer science. I encourage all of you to watch those YouTube videos just so you can see how these things interact with each other, to give you a sense of why you're in this course. Okay. Now, so that'll be it for today. I will post your first homework assignment, if not today, tomorrow. Everyone try to get the textbook, install Python, start playing around with it, watch the YouTube videos, and I look forward to the semester. Now, attendance to these Zoom meetings is not mandatory. I think the homework will be due next Wednesday. I might change it, but at the earliest next Wednesday. So attendance to these Zoom meetings, it's not mandatory, but I highly encourage you to attend them so you can ask questions with me. It will also help me be a little bit more engaged in my video lectures if I have at least a few people here to talk to. Otherwise, I feel like I'm just talking into a void. So please, at least a few people show up. Okay. All the due dates will be available on the ZyBooks textbook. When you log on to your textbook, you'll see the due dates and when you'll need to turn everything in.
You mentioned logging into our textbook. What do you mean by that?
It's just like signing into it. So let me share my screen.
So I buy it from the library, right? Or not the library, the bookstore?
No, you just go online. So here. Okay, so here's my screen. So you go to learn.zybooks.com and
Okay.
in this code, and then you purchase the book. And when you purchase it, you'll be able to pull up something that looks like this. And you'll sign in, and you'll have your textbook. And then there will be assignments that will be posted. I guess for today, since we didn't really get into any of the content, I would suggest reading sections 1.1 and 1.2 before next class. And that'll prep you for that. Okay. All right, so there's a group me. Everyone join that so you can get a hold of me whenever you need.
Professor, can you show the code for the book again on Blackboard? I missed it.
Oh, it's right. If you go to Blackboard and you go to the Discrete Math Sidebook information, you'll see the code right underneath it. It's UHD Math 2305, Davila, Monday, Wednesday, Fall 2020. So as far as my video lectures go, I'm going to make a folder, and I'm going to put all my video lectures in there, and they'll be able to view them the entire semester. Okay.
You also mentioned signing into a group. What was that? I missed that. I must have missed that. I'm sorry.
That's okay. If you look in the group chat a little bit up, you'll see a link. It's a group me thing. Okay. I don't know if you ever used that before.
No.
Just a way to communicate with everyone in the class.
Oh, cool. Okay. Okay.
With your phone.
Thank you.
Okay.
So right now on ZyBooks, it says no current assignments, but they'll be uploaded later, right? So we just do the reading for now?
Posted either today or tomorrow morning.
Okay, thank you.
Yeah, I'm joining the group meet right now. I'm in. All right, guys. Nice
Thank you.
to meet everyone. Everyone stay safe, stay healthy.
Thank you.
And let me know if
Thank you.
needs any kind of special attention. I'll try my best. All right, and that'll be it.
Bye.
Bye, everyone.